also for collecting data.
Oh, okay. Is there a click?
You can use mine.
Oh, you can click. Yeah. Well, if we're going to all give presentations in the same time.
It's mine. Welcome to the 12th state planning session, and Felipe will first.
Okay, I'm going to present a joint work with Manuel Veloso, my advisor at Carnegie Mellon University. Before I start my talk, I have a quick announcement. So unfortunately, the version of our paper in the thumb drive and the CD runs the wrong version of the paper. So if you see this picture in the front page, you got the wrong version. In the online proceedings, we have the right version. Or you can just Google short-sighted SSP, and you're going to land in my page or in the right version of the paper. So, on probabilistic planning, we have two classes of solutions, right? One is the complete policy, that it's a mapping from every stage to an action. And the good thing about the complete policies is that it will never fail. If you give this complete policy to a robot, the robot, no matter where you end up, will always know what to do. The other thing that is good about complete policies is that they can be optimal. The bad thing is it does not scale up. The other class of solution are the partial policies that map some states to action. So the bad part of it can fail. So if you give it this partial policy to a robot, the robot might reach a state that is unpredicted, and we might need to replan, might need to call the planner again. The other thing is partial policies are non-optimal, but the nice thing about the partial policies is that they scale up really well. It's computationally efficient to find one. So in this talk, I'm going to present a framework that gives a new trade-off between complete and partial policies. And this framework is composed by two parts. The first one is a new model that we call the short-sighted stochastic shortest path problems. The second part is a new planner that we call the short-sighted probabilistic planner. So here's the big picture of my whole talk. So we're going to model our problem as a stochastic shortest path problem. So we're going to have an initial state and a set of goal states. Then we're going to generate these short-sighted subproblems that basically are going to represent by this cloud. And what we're going to do, we're going to take everything that's outside this cloud in our search space, we're going to throw it away. We're going to focus only what's inside. And throwing away is not a good idea, but we're going to keep some information from what we throw away by adding an heuristic. So we're going to attach to each state on this border of this cloud an heuristic value. And I represent that by the different shades of green here. So the greener, the closer will be to the goal. It depends on the heuristic, of course. Then we're going to solve this short-sighted subproblem, and we're going to get a complete policy for that. So we know we're not going to need to replan there, and we're going to execute this solution. And then once we get to the border of this cloud, we're going to iterate. We're going to do that again and again until we reach the goal of our original problem. And then I'm also going to show what we can say about this single execution case. And also what we can say about if we have a simulator, for instance, we are not executing the real world, and we can simulate this problem from the initial state to the goal state several times. So now I'm going to give a little bit of a background. So this is my definition of stochastic shortest path problems, or SSPs. We have a set of states, initial state, a set of goal states, set of actions, transition probability function, that's the probability of moving from one state to another when you apply an action. And we have this cost function that's going to be the cost of applying action A on state S and reaching the state S prime. This function is always going to be greater than 0, and we require to be defined only if this transition is defined, so if the probability is greater than 0. This example here is going to be my running example. So I'm always going to show the initial state has this gray shade of state, and then the goal state always going to be green, and I'm going to always attach the probabilities in the arrows. So also, by an optimal policy, it's going to be for us, the policy that minimizes expected cost to reach a goal state from the initial state S0. And the minimum expected cost to reach a goal state is given by V star, the optimal value function here. That's going to be 0 if you're in the goal state. Otherwise, it's going to be the minimum over the actions of the expected value of applying that action and solve the problem from that state. So here's a little bit a more formal idea of what are short-sighted SSPs. So we are in the business here of managing uncertainty. Our search space is too large. And since we have probabilistic effect of actions, there are some parts of our state space that might be very unlikely to reach. So since it's too large, we cannot look at it all at once. So we're going to consider only the neighborhood of our current state that I'm depicting here by this circle, and we're gonna we're gonna prune everything that's outside, and we're gonna put every single state in the ring of the circle. We're gonna call them artificial goals. So the short-sighted SSPs are gonna be SSPs, but they will have these artificial goals. And we're gonna attach an heuristic to these artificial goals that's gonna tell you more or less what is the expected cost to reach from one of these states, the original goal. And formally, we're gonna define the neighborhood of a state using this function delta that basically counts the number of actions to reach one state from another. So delta of S to S prime is just the minimal number of actions to reach S prime from S. Now being completely formal, so if you give me an SSP, you give me one state S, and you give me a value of t greater than 0 in a heuristic function, my short-sighted SSP for these parameters are going to be a new state space, S prime, that are going to define as all the states 0 S prime in the original space, such that I can reach S prime from S, that's one of the parameters, using at most the actions. Then I'm going to change the initial state to the state that you gave me S, and I'm going to change the goal states, the goal set. So now the goal set is going to be all the states S prime that are reached using exactly T actions. So it's going to be all the people in the ring of the circle. Then the structure of the actions are going to be exactly the same. I'm not going to change the actions, I'm not going to change the probability transitions, and I'm going to change the cost. So now the cost of applying action A on state S going to S prime is going to be exactly the same as before, plus the value of S prime in the heuristic if S is an artificial goal. If S is not an artificial goal, is not on that ring of the circle, then we're not going to change anything, right? And here's some examples. So here the running example again, the very same, and here's the delta function from S0 to all the other states. So S0 to S0, you don't need to apply an action. To S1, you can get with one action. To S3, you can get with one action. To SG, you can get with one action. And S2 is the only one that you need two actions to apply. So if we look at the short-sighted SSP, starting from S0 for t equals 1, we're going to get everyone here that has value 1, and we're going to put them as artificial goals. So SG was a goal, we keep it there as a goal, and then we have these two artificial goals, that's why they're dashed. So far nothing really interesting, but if we increase the value of t to 2, then we're going to have this. So now only S2 is an artificial goal. And we keep the original goal because we could reach with 1. And look that now here the back part of that example is represented perfectly, right? So we have all the action structure here, even though I can reach S3 with more than 2 actions. I could go from S0 to S3 and keep looping here. We still will not count this as an artificial goal because we can reach it with 2 actions. 2 actions, that's the minimum. So you might have a question right now in the back of your mind of, is this look-ahead search, or how does it compare with look-ahead search? So again, the same running example, and here is the look-ahead search from S0 using t equals 2. So what we are doing is, what are the states we can reach using up to t actions? So from S0 we can go to S3 and S3 again, right, on this example, and this is how the look-ahead search works. So now I'm going to replace the original problem here with the short-sighted SSP from S0 and t equals 2. So what happened is, we put this state as an artificial goal. So just staring at the two pictures, you might be able to already say, what is the difference? So the difference here is, look ahead is giving us a 3, while short-sighted SSPs are giving you a graph, or a multi-graph. So, and is this really a big difference? And the answer, yes, it is a big difference. So if you think about the look ahead, once you look at the state S0, it's saying you can go to S3, and then you go to S3 again, but then it doesn't say anything else. On the short-sighted SSPs though, you know that from S0, you can go to S3, and you can keep there on S3 for a really, really long time, especially because the probability there is 0.9. So you know that you can get trapped there. And since the optimal value function is looking at an expected cost, so you're in the business of doing these expected values, that once we are talking about loops, they're infinite sums. So what look ahead is giving you, it's an approximation of this infinite sum by taking the first t parts of this infinite sum, while on short-sighted SSPs, we keep this whole infinite sum. So here, we are simplifying the horizon, and here we are not. We just simplify states, we keep the same horizon, and we keep the structure of actions. So this difference is so important that in the paper we have this proof. I don't know if you guys can see from the back here, but basically what you're saying is, if you compare look ahead from the same state using t, or given value of t, and short-sighted SSP starting from the very same state and the very same value of t, we are going to give you a value bound. We are going to give at least the same value as the look ahead, but if there are loops, we're going to give you a value bound. And since we're talking about cost, a value bound means a larger bound, and both of them are going to be bounded by the optimum value function if you're using a reducible heuristic. So now that I've told you what is a short-sighted SSP, I'm going to present our planner, the short-sighted probabilistic planner, or as we call SIP. So SIP is a very simple planner. You might even call it a meta planner. So what we are doing here is, you start from your initial state, you're going to generate a short-sighted SSP. You're going to take the short-sighted SSP, compute the optimal policy, and here you can use any optimal solver. You pick your favorite. And you might be thinking, well, you motivated this talk saying that complete policies are hard to get, they do not scale up, but it's okay. The short-sighted SSPs encompass a really small part of your problem, so it's okay to get a complete policy there. And then once we have this complete policy, we are going to execute it until we get to a goal of the SSP. If it's a goal of the original problem, you're done. And if it's not, we're going to iterate that again and again and again. So now I want to show what's a guarantee we can give for this particular strategy of applying SIP. That's when you do that only once and you execute this action in the environment. And the guarantee is for at least T actions, you can execute at least T actions before replanning. So basically what you're saying is, since you construct these short-sighted SSPs, looking at all the actions, all the states that you can reach using up to T actions, you know that you're not going to replan if you get a complete policy for them. But that gives you the bound of T. But how we can get the at least T, that comes again by the fact of the loops. So in this example of short-sighted SSP, if our optimal planner gave us this policy on S0 apply A1, on S3 apply A2, we can apply this policy for more than 2 steps. For instance, we can go from S0 to S3 and keep track on S3 for an indefinite amount of time. This again showing that we are not simplifying the horizon of the problem. We can still stay there for an indefinite amount of time. You give me any amount of time, there will be a non-zero probability of getting trapped there. Now, what if we run SIP multiple times, right? So there are 2 scenarios. Imagine that we have a robot. The robot is saying the same problem over and over again. Or the more common scenario is now, instead of executing the environment, we have access to a simulator. And someone gave us a budget of time, saying you have 20 minutes, and you have access to a simulator. You're going to simulate this problem until you reach your budget. Meaning, once you get to the goal of the original problem, you start it again from the initial state. So then we have this theorem saying that SIP will be asymptotically optimal. Meaning, if the same problem is solved sufficiently many times, then the optimal policy is always found. And the intuition behind it is, let's suppose that this is the first solution, the first run of the problem. So these are the short-sighted SPs that we generated. The red line is the execution. We got to the goal. Now when we're going to solve the second time, we are going to get some information about the last execution, and that will help us to change the bias. I'm not so sure if you can see the different shades of green here, but basically the last execution is changing how we are biasing the solutions inside the short-sighted SP to reach the goal a little bit faster. So if you know real-time dynamic programming, RTDP, basically we are giving the very same guarantees that RTDP gives you. But at the same time, if you know RTDP, you might be asking, well, how does it differ from RTDP? How does SIP running on an anytime setting differs from real-time dynamic programming? So both of them are asynchronous value iteration. And the real difference is the scaling of the BEM updates or the BEM backups. So just to illustrate this difference, let's suppose that every time that I make a backup, I'm going to put a yellow dot here in this search space. So if you look at the RTDP, we're going to basically run one trial of RTDP. We're going to get one path from the initial stage to the goal, and we're going to make backups on this line. And then, if we do another trial, it will be another line, next try another line, and you will get the drill, right? After a long time, we're going to cover a huge region, and we're going to extract the optimal policy from this region. So, how does SIP work then? So, we're going to generate a short-sighted SSP, and then we're going to solve it. Let's say we're going to use RTDP to solve it, the very same algorithm that we use in the other side. So we're going to run one trial of RTDP, we're going to do this one short line, because now we're not going to the goal, we're stopping the artificial goal. We're going to do another line, and again, you get the drill. We're going to cover a whole region here. And then we're going to execute or simulate our solution, get a new state, and do that again. We're going to get another block, and do that again until we reach the goal. So the difference is, RTDP, you're going to fulfill this region by doing these very thin lines, while your SIP is going to choose a block, solve the block, do a lot of lines in this small block. They move to the next block, do several lines on this small block. And as I'm going to show you in the next slides with the experimental result, this is enough to get improvement in the performance on top of the algorithm that we use as the optimal solver. Meaning, if we use RTDP, we're going to get an improvement on top of RTDP. So, in the experiments, I'm going to compare SIP against the winners of the previous probabilistic competition. And the setting I'm going to use it is the setting from the first and the second one, the IPCC 2004-2006. And basically it boils down to the following. For each problem, the planners are requested to solve this problem 50 times in 20 minutes. And learning is allowed between the attempts. So everything that you can infer, or you can learn, or you can keep track of, you can use it again for the next attempt. And the evaluation metric is going to be the number of times the goal is reached over these 50 times that you have to solve it. And here are the planners I'm going to compare with. I'm going to compare SIP using LRTDP as optimal solver. I'm going to compare with LRTDP by itself, then FF replan the first place of 2004, FPG first place 2006, or FF first place 2008. And the parameters for SIP is I'm going to use T from 1 to 10, and the heuristic is going to be the zero heuristic, FF plus all outcome determinations, and the mean mean. For LRTDP, I'm going to give the same set of parameters, except that T I'm going to allow to be from 0 to 10, and for LRTDP, T means the look ahead. So every time that LRTDP has to do a greedy decision, it will use this look ahead. If T is equal to 0, no look ahead, is a vanilla LRTDP. If T is greater than 0, it will use that look ahead search, will find the best lead, and gives a decision on that look ahead tree. So here's the result for the triangle tile board. So I'm giving you two flavors of SIP. The blue flavor here is going to be the same throughout the plots. There will be T equals 3 and the FF plus all outcome heuristic. The green bars are going to be different for each one of the domains because we are picking the best parameter for that specific domain. For LRTDP, the yellow bar is exactly the same. You're giving the best parameterization for LRTDP in that problem. So what we can see here is SIP, the green one, with the LRTDP, the yellow one, both with the best parameterization for that specific domain. SIP performs much better, and scale up is much better. You see how we slow down very slowly while LRTDP goes down really, really fast. And the only difference here is how we're scaling our backups, and we scale up better than the others. So that was our best case. So here's the other case, Bloxword. Again, we perform better than LRTDP, but what's happening here is the green one changed, as I said, now it's 2 and FF heuristic. What is happening is we do quite well until problem number 8. For the larger problems, we just get lost. If you're familiar with Bloxword, there's a ton of non-optimal solutions inside, and we get lost trying to find a solution there. Now, going to the exploding Bloxword, that basically is a Bloxword with dead ends, where blocks can explode. So what happened here? We have an improvement up to problem number 9, coincidentally the same number as the other one. So if you see the problem number 1, we improved upon all the others, a little bit better than LRTDP. In this case, the blue and the green curves exactly the same parameterization. We improve it, we tie, we never lose up to problem number 10. It's a small tie, maybe not relevant. But for problem 11 and so on, we don't perform well. And what's happening here is the probabilistic interesting part of the problem, once it's done, once the Borden blocks are detonated, what is remaining there, it's a block's word. You have to move the blocks in the way you want, and we know you're not great on block's word, unfortunately. And here's the last domain, kind of the borderline of my time. So in zero travel, we improved a little bit upon the other planners. And here's the summary of the experiments. So the blue curve that was SIP overall, the same representation over all the domains, we outperformed all of the other planners on 16.6% of the time. We tied with the best on 41%. If we optimize the parameters for each one of the domains, we outperform them on 36% of the time, tied with the best on 53% of the time. There's two interesting remarks here. The first one, SIP is never the last place in the planners, meaning you're not going to get the worst performance in any one of the experiments we've run so far. And the very nice one is LRTDP never outperform us. So we tie or we do better. So basically what I'm saying here is just changing that scheduling of the down updates got us improving the performance. So to conclude, I present you a framework that presents this new trade-off between complete and partial policies. And to do that, I introduce short-sighted SSPs and SIP, this new planning algorithm that you can use in two flavors. I have two flavors of SIP. SIP has a replanner where we can give you the guarantee that there is no replanning is needed for at least the actions. And then you can use it as an anytime algorithm that is exactly the very same guarantees that RTDP gives you. And as for future work, we are looking at new definition of short-sighted spacing, that S prime. How can we define that differently? We have already some ongoing work on that. And to improve the scalability on the non-probabilistic interesting problems. For instance, Blocksport, when you have several non-optimal solutions, can we just ignore the probabilistic interesting part of it? There's no dead ends. Can we just get a cheap solution out of that? And basically that is. Thank you.
So in your paper you say that you require the reachability assumption. How is it fair to compare on exploding blocks world then because it has dead ends?
Yeah, so it's the same requirement for LRTDP, right? So in the sense LRTDP we require the very same thing. So with LRTDP we're really fair. And that requirement actually is to find the optimal policy, right? If you don't have that, we are not guaranteed to find the optimal policy. We're not even guaranteed to finish a trial. But in practice, we finish a trial because we have a threshold there in the cost. So if you cannot reach anymore your goal state because the block that you needed, let's say the table exploded, and the table was not supposed to be exploded, you're going to move blocks around. At some point, the cost will be very large, and you're going to say, okay, that's too much, that's a dead end, let's start it again.
Yeah, but if there are dead ends, unavoidable dead ends, your heuristic functions is infinite. So normally, in such a case, the criterion is not well defined anymore. There is no optimal policy. You can choose one.
Yeah, so if there is, that's exactly the case of exploding blocks work. So if you see all this problem here, it's not that we're not getting the optimal policy there. I'm not sure about this first four, but at least the first two, I check it by hand. There is no policy with probability 1 to reach the goal. So what's happening there, since we're not giving infinite cost, we have a threshold, in this case it's 500. Once you get there, eventually some policies will not diverge to 500, some will, and you don't have time enough for all your policies in your initial state to diverge to 500. So because we have this budget of 20 minutes, we give like solutions until you get.
And that's something, all policies have the same infinite value. How can you compare policies that are equal to infinite?
Yes, in this case, sorry if I didn't explain well, that's exactly the case of these four problems. All the policies there has infinite cost because there's no probability 1 policy to reach the goal. But the thing is, for these problems, we're not in the business of finding the optimal. We cannot even get close to the optimal. So we don't have time enough to diverge. That's the thing, right? If you give me like 3 days, then probably all my policies will diverge. But since we just have 20 minutes, none of them diverged, and we gave as solution whatever we thought was the best for that threshold. But I agree with you, there is there's no cost to find it. If you see the V start of 0 is infinity in this province, except let's say the number 5 and the number 7. There are probability 1 policies to reach the goal there.
So do you define a count of letters for every policy?
Oh,
Yeah,
okay.
yeah, thanks.
Any questions? Well, I think I'll play actually. Okay, ask while we're switching. Yeah, you can ask. Ask
Yeah,
while
when you generate your short-sighted estimate, are you computing the heuristic value systematically on the entire fringe of the SSP?
No, yeah. I guess what I mean by systematic is doing it smart. Yeah, we are doing it smart. We are just asking for the heuristic value where it matters.
Okay.
We are not computing the heuristic value at all. Then being of that after heuristic will be really costly. So, we just basically, we define what is the fringe, and every time we touch a fringe one, we query for the heuristic.
Okay, let's let Thomas go. I'm really interested to hear about this paper. I've waited. I've waited 1 year to hear about the winner of the public. This is here. So I waited 1 year to hear about the winner of the public planning competition last year, and this is the paper in the plan.
Thank you. Okay, so hello. I'll be talking about the probabilistic planning system Prost, which was developed by Patrick and myself. And yeah, how did it come to be as it is? It was actually sometime in 2010 that we finished working on the Canadian travelers problem, where we compared several algorithms with each other. Among them, determinization-based replan approach, and we realized that it actually pays off a lot to use an algorithm that takes probabilities into account. And the best algorithm we implemented back then was UCT. Around the same time, Scott announced what is going to happen at the IPPC 2011. One announcement was that there will be a new input language, Riddle, which was created to be able to model domains that are probabilistically complex and therefore hard for the determinization-based replan approaches. So we kind of put this together and decided, well, okay, let's just try to do the same things we did with the Canadian travelers problem and apply it to domain-independent planning. So this talk will be based on the several components that are incorporated in Prost. I will very briefly only talk on UCT. I think most people know what UCT is. One thing that is mostly due to the structure of Riddle that showed to be very successful is the reasonable action pruning. What we also implemented is Q-value initialization, which was also something that is very important in the Canadian travelers problem. I will briefly talk on search depth limitation and at the end a method to detect reward logs, which are usually goals or dead ends. Okay, so UCT is a Monte Carlo tree search approach developed in 2006 by Koschitz and Sepesvari. In UCT performs rollouts in a search tree which consists of two kinds of nodes, decision and chance nodes. And in decision nodes, well, there are in both nodes you have different rules how to choose the successor. In the decision nodes, there are basically two cases. If a decision node still has successor nodes that have never been visited, UCT will choose any unvisited successor randomly. And if all successors have been visited at least once, it will apply the UCT formula, which is there to balance exploration and exploitation, and choose the successor that maximizes that formula. In chance nodes, these are basically the nodes where the outcomes of actions are determined, and there you just sample. So you pick the outcome with the correct probability. Moreover, UCT is an online algorithm, which means, well, you can also use it as an offline algorithm, but we use it as an online algorithm, so we always only compute the next step, and we are not interested in the whole policy, but we compute one step, we deliver the step to the environment, we get the outcomes from the server, and then this goes on until until the finite horizon is reached. Okay, reasonable actions is something that is in very many of the IPPC domains actually, which is mostly to the fact that in Riddle you don't really have action preconditions, but you can model preconditions indirectly by using state action constraints. But for IPPC 2011 it was announced that we will only use static state action constraints, which means that either something was always illegal or it was always legal, which was mostly used for concurrent actions. So basically most actions were always legal. There were just some combinations that were not allowed. But nevertheless, of course, there are very often actions that just do not make sense in very many states, and this basically leads to the fact that actions may have identical effects. Most of the times they have the same effect as just applying the no-op action. And yeah, that led to our definition of reasonable actions, and especially the reasonable action pruning, which we do that if multiple actions lead to the same probability distribution over successor states and to the same rewards, we just prune all but one of them. So I'll have a little example here. This is actually the elevators domain from the IPPC. Here we have an open elevator at the bottom floor which directs up, and we have one person at the first floor waiting who wants to be delivered to the second floor. In the elevators domain it's made in a way that the elevator can only move if it's closed, and opening the doors you also decide if you want to change direction. So if we look at the probability distribution of the successor of applying the no-op action here, well then obviously the elevator will still be where it was, it will still be open, the person is still waiting, and additionally we have a 12% chance that another person arrives at the first floor who wants to go down. If we now look at another action which is called open door going up, well, as the elevator is already open and as the direction is already upwards, it will lead to exactly the same probability distribution. So basically, no different things happen here. And the same is also true for moving the elevator. It won't move because the door is not closed. So basically, rather than making rollouts and choosing all three of actions, we can prune two of them. And this is actually something that happens in almost all of the domains, actually in all but sysadmin. Sysadmin is the only one where there are no unreasonable actions. But as you can see, there are 4 domains where more than 50% of the actions could be pruned. And yeah, the reckon at the bottom where you have a rover and have to use instruments on some planet, actually almost 80% of all actions could be pruned by this approach. Okay, another thing that is quite important for UCT is, the authors of UCT actually state that in the limit, UCT converges against the optimal policy. The problem is, of course, time is limited, so this in the limit will never actually happen. So a very important part for UCT is to focus on the relevant parts of the search tree. And there are actually 2 things that we were working against. The first one is what we call UCT is blind, more or less, which is due to this rule that in a decision node, if a decision node has unvisited successors, UCT will randomly choose any of them. And because this happens especially initially very, very often, it takes quite a long time that UCT just performs random walk in the search tree. And that means that convergence is really slow. So what we do against this is that we initialize the successors of decision nodes with some Q value. And in PROS, we did it in a quite straightforward way. What we did is we used the most likely determinization and an iterative deepening search. And we compute a Q value estimate for all actions in a decision node by applying the iterative deepening search up to a depth that is learned initially, or up to a depth when we estimate that the quality of the result is actually already sufficient. And yeah, and finally we create decision nodes with that value, and also add some virtual rollouts to each decision node, so that the rule that a node is chosen randomly will never apply. We will always apply the UCT formula. Okay, I will show some first results here on this. All these numbers are actually IPPC scores, which are normalized to a value between 0 and 1. We had a baseline planner running with it, which was the max, the better of the no-op and the random policy, which usually got 0 points, and the best competitor got 1 point. So we compare all the results I will present here. There will be more later, and the Klatten planner of Andre here. And yeah, it can be seen that especially in the domains where it's very important that a correct sequence of action is taken, like for example in the elevators domain, where the planner must find out to close the door, to move, to open, and to change directions. The Q value initialization is really, really important. For example, in elevators, without implied UCT, it's almost as bad as a random policy, while initialized it's already quite good. Another, well, it might not be a problem, but something that we investigated was that decisions that are quite far in the future, that are far away from the root node, actually have less influence on the next action that we are going to pick. So what we did is, in order to get more rollouts in the same amount of time, we wanted to make them shorter and stop after a couple of decisions. We actually stopped after 15 decisions, and there are many possibilities how you can stop. Often, I don't know, like for example, the Cadia player finishes with a random walk at some point. You could apply evaluation functions when you reach a leaf. What we did is we just stopped, because the way IPPC 2011 worked was that every action actually resulted in an immediate reward. So we already had a quite good estimate on how good what we did until that point was. So there was no need for us to actually estimate how much more reward we will get in the future. Obviously, this is not optimality preserving. There were actually 2 domains where we had some problems due to this procedure, but in general it paid off. And as you can see, there are a couple of domains where things get better, traffic, again elevators, but there are 2 domains actually. Crossing traffic is not so bad, but navigation, it was quite a bad decision to implement, to use this, because navigation, the policy that used to be optimal in the whole horizon is not any longer optimal in one where we limit the search depth to some value that is smaller. So for that reason we got worse results here. Actually, these 2 domains where our results got worse also have something else in common that is special among them. They're both goal-oriented domains, and they're both domains with dead ends. Not dead ends in the sense of that nothing is applicable anymore, but dead ends in the sense that no matter what you do, you can't get a good reward anymore. So, which is something that we observed, and so we tried out what could we do with that information. Can we somehow realize that there are states where no matter what we do, we cannot improve our policy anymore or get worse? If we can we somehow check that? And for that reason, we introduced reward loss, which is, as I just described it, basically a state where no matter what you do, you will always end up in a state that yields the same reward. No matter what you do, which is usually either that some goal is reached or that a dead end is reached. And what we do with the reward logs is actually that we can stop our rollouts even earlier than at the search depth limit, because we know no matter what we apply, we will always stay there in states with the same reward. And additionally, we penalize dead ends and reward goals. So in general, the detection of reward logs is not a simple problem. So what we did is we made an approximation procedure, which works as is described here. We first calculate some reference reward in the current state. You can use any action and any successor state for that, because anyway all actions must have the same reward for it to be a reward log. Then we add that state to some closed list, which we implemented as a BDD. What we do then is we apply all actions, we do not really apply the actions, we calculate successors in a 3-valued clean logic, where values of 0 and 1 stay 0 or 1, and for variables which yield a probability distribution, we just say that the value in the successor state is unknown. And the reward function on this kind of states is as the usual reward function, unless some unknown value is evaluated during it, and then we will also yield an unknown reward, and it will not be a reward. After we did this for all actions, we actually merge all the states together to one successor state. Again, if two states that are merged have the same value for some variable, it stays that value. If they have different values in the merged state, it will be unknown. And if this resulting merged state is already in our closed list, we found a reward log. Otherwise, we repeat with this state and iterate until it returns true or false. Okay, I also have a small example to illustrate how this works. This is the crossing traffic domain, which is basically the game of Frogger. In the middle frog, and there are, with some probability from the right side, obstacles coming on some road. And let's suppose that the planner just samples some rollout where it decides to move north, and the outcome is actually that a car is hitting the frog there, and the question is, well, now is this a reward log or not? So what is happening then? First of all, basically the frog will be removed from the grid then, and all actions have no more. Then there's only one reasonable action left, which is the no op action. So what we do now is, well, we calculate this clean successor state of the one where the frog is missing. The two cars that are present still proceed one step to the left, and on the right side, where we get a probability distribution that the car actually is there, we will have unknown values, which is why the cars are a little grayed out there. And we will continue with the algorithm. Now the middle row is also unknown, because those values actually depend on the values of the right row, and we proceed like this, and then finally we will stay in the state, and we know, okay, we have found a reward here. This is, as I said, we store our reward logs in BDDs in the planner, and we use those BDDs to find out quicker if we are in a state that we have labeled earlier as a reward log. And this is actually the crossing traffic 1 example. Only after a couple of rollouts, the planner already has the whole dead end. It found out all the dead ends. The O's basically mean the position of an obstacle. The R's are the position of the agent. And this BDD basically says it's a dead end if the robot is nowhere, or if it's at the same position as an obstacle. Those are exactly the dead ends in BDD. And there's a similar BDD for the reward, which for the goal, which is a bit smaller, which just says, well, if you're at the top row, you're in a goal. Okay, so these are basically the final results I want to present. As you can see, the reward log detection mostly pays off, it can only pay off in the two domains where we actually have reward logs. In the other domains, things get slightly worse, but not too much. It's not in general, because this procedure takes some time, so we have a bit less rollout. And on the right side, we also compare to Clubben. At least these are the results Clubben had in the IPPC. I think the very improved the results so far, but these are the results that they had in the IPPC. And as you can see, Prose is able to outperform Platten in all the domains besides the navigation domain. Some words on current work. We are actually right now also looking a bit more into this reward log detection, because we actually realized that especially goals are really more often even in the domains than we thought they are. First of all, if the definition is slightly changed, then actually 3 of the 8 domains already have in the probabilistic version something that could be called a goal. And even more interesting, in the determinization, 6 of the 8 domains have goals. So that is something where, well, the simpler thing is that we can obviously stop the iterative deepening search earlier. If we at some depth end up in a goal, we know, okay, if we add 1 depth, we will again end up in the goal, and we can just add the reward of that. But something that might be really interesting is that we want to look into deriving really goal descriptions from this procedure, and then apply classical goal distance heuristics from classical planning and see how that works out. Okay, so to summarize, I presented the Prose Planner, a domain-independent probabilistic planning system, which is based on UCT. And I showed how to combine it with some additional techniques, reasonable action pruning, Q-value visualization, the search depth limitation, and the reward log detection. Okay, thank you.
Okay, so we have some questions.
Just to make sure I understand, so computing the reward logs is essentially computing strongly connected nodes in the graph, is that right? In the transition graph.
Yeah, yes, you can say so.
But isn't that, it's a insistent domain, right? Huge state space where you can get from any state to any state essentially.
Well, what we do is we have this over approximation. So I mean, it's not that we will find out all the reward logs. There are reward logs that we cannot detect because we check basically in more states. We just say, well, by using those unknown values, we make sure that it's actually a fast computation.
Okay, so you can generate something that's not actually a state in the process.
No, basically we describe states in this clean logic. So rather than saying, okay, we have complete states consisting of 0 and 1, we also allow the unknown value. And we basically describe state sets with that.
How did you tune your UCT parameter, especially the C parameter?
The bias parameter, we actually set the bias parameter to the current estimate in the rollout. So in the very first rollout, you don't need that bias parameter. And after that, whenever we start a rollout, we set the bias parameter to be exactly like the estimate of the rollout.
So the Q value basically.
Yes.
So by the way, you can set C to essentially the current distance from the end of the process, just horizon, and everything will...
To the reward that has been gathered in the...
No, to the distance. I mean, C is the thing that regulates the strength of the exploration time. Yeah.
That is 1 actually. Yeah. We keep that constant on 1. I think.
That is supposed to work only if all rewards are between 0 and 1.
Okay, no, but then I was talking about that parameter you were asking. We set that one to the Q value of the current reward.
Yeah, that is logical because this C parameter has nothing to do with the horizon. It only comes to calibrate the range of the random variable. That's it. The sole purpose of C is to overcome this, as you said. You have the inequalities built from values with 0 to 1, and if you have between 0 and 1 million, you have to calibrate it, otherwise it's apples and oranges.
Okay.
Similar question, how do you choose search depth?
We set it to 15. It was just empirically, we do not have any dynamic system currently for that. It was just an empirical process.
something except for UCT tried in the lab, like MC algorithm, bots, and something?
We started to toy around a bit with other things, but actually we are not at the point currently to say if something better is better or not. So, I mean, not really.
That was
not
yours.
yet. Yeah.
So,
How do you initialize a web function?
We use a most likely outcome determination, and we apply an iterative deepening search where we initially learn some value of the maximum depth for this iterative deepening search, and that's what we do.
okay, so just one quick question. So you said in 6 of the 8 domains there was some notion of some abstract notion of goal. For elevator system in traffic, I wouldn't see that, right? I mean, these are process-oriented problems.
Only in the determination. So in elevators, for example, in the most likely determination, you will end up at a goal if all the passengers are smart. Because with determination, no new passengers will arrive. It's the same for suicide. I mean, if all computers are running, as none will research traffic or determination, we will reach the goal. So actually, all the goals also make sense. And it's really something that is
Okay, that's quite cool.
Ideal situation.
Great, okay, let's take our speaker. Next up is Andrei Kolobov, sort of a close second of the competition and probably has lots of follow-on work that you'd rather talk about now. But you can go to UAI or IIII for that work. I'll mention.
Last year that Hyundai, Masterman Development submitted. Just first to give you an idea of what kind of challenges we were facing when we were trying to come up with planning technology for this competition. Here is an overview of the state of the art, so to say, before IPPC in 2011, prehistoric times, and how it changed with IPPC. Right, so in prehistoric times, the probabilistic planning community was mostly concentrated on solving goal-oriented MDPs. Okay, these MDPs had small branching factors mostly because we couldn't really express MDPs with large branching factors. And the optimization criterion that determined the winner at the International Probabilistic Planning Competition used to be the probability of reaching the goal of the policy that your planner produced. Okay, now notice that this optimization criterion is easier than the optimization criterion that we typically are interested in when solving goal-oriented MDPs, which is the expected cost of reaching the goal. Okay, so this is slightly easier, and there were two broad classes of approaches that these problems were solvable with. One, well, heuristic search methods like LRTTP, LEO star. Since you didn't care about cost much, you could initialize them with an invisible heuristic, which would make them quite informative, and often they would succeed. In more scalable class of approaches, and the ones that became the trend over the past few years were the optimization-based planning algorithms. And those essentially will convert the problem into a probabilistic problem, to a classical planning problem, and then when you're trying to decide what to do in a given state, the classical planners would essentially find a path, several paths to the goal, and sort of show you the direction where to go, okay, where the goal is. And this is the high-level idea. There are many details, but this is roughly how classical planners used to help to optimize for the probability of reaching the goal. Now, in IPPC 2011, we're faced with reward-oriented MDPs, finite horizon MDPs with large horizons and also very large branching factors. Scott introduced this nice language, RDL, that finally let us express those, and pretty much all the problems essentially had big branching factors, meaning either many actions or high average number of outcomes per action. Now the optimization criterion became harder as well. It became essentially the expected reward of the policy. And to optimize for that, you essentially need to build a much more sensitive, sort of much more fine planning technology. So if we look at whether we can solve these new MDPs with old methods, we'll see that, well, heuristic search doesn't really work, at least in the way it used to exist, because with huge branching factors, you need to perform Bellman backups over a huge number of states, right? You need to Bellman backup. And for some domains, it can be done with symbolic approaches, for instance, but definitely not for all. Can it be done with deterministic-based planning? Not really, because the main reason why determinization-based planning used to help, which is showing the way to the goal, isn't applicable anymore. But it's trivial to reach the goal in finite horizon MDPs. Every single trajectory essentially goes to the
So by heuristic search here, you silently assume complete heuristic search.
Yes. Optimal. Yes. So again, the main reason why classical planners used to help is now gone. Right? So for this computation, we essentially needed to build planning technology by either significantly modifying something that used to exist or coming up with something new. And the objective was to build a scalable planner that has good anytime behavior, right? Because we're still under time pressure, capable of dealing with finite horizon MDPs with large branching factors, long horizons, and be able to produce decent policies in the presence of these complications. And it's a kind of a self-imposed objective, as opposed to the previous ones which were imposed by the competition, more or less, is to produce something that generalizes, that can be easily generalized beyond IPC problems. Now, what do I mean by that? Most of the questions about UCT, about Prost, as you just heard, were about, well, how do you treat all these parameters that UCT has, right? Many of them are very, very much problem set dependent. Like the look ahead, for instance, that was set to 15. Well, its value, as you saw, it worked for many problems, but for some it didn't. And it doesn't generalize easily. Same thing with many other parameters that UCT has, for instance. You know, the weights you assign to the initial heuristic values, and so on. All these values, you know, can be, again, domain independent, and therefore, if anybody wants to take a planner and apply it to someone else, you know, they have to try very hard to find good ones. Even though if they do know good ones, it's going to work well. We wanted to avoid that. We essentially wanted to produce something that works out of the box or almost out of the box. Has maybe a few parameters that are very easy to tune. Okay? And our response to these challenges was a planner called Glutton. That's essentially centered around the idea of reverse iterative deepening. We modified the LRTDP algorithm that used to exist before to use this new idea that I'm going to describe. We also did some optimizations to make the process, essentially the planning process, more efficient, like subsampling the transition function to deal with large branching factors and so on. Again, I'm going to talk about all of this. But first, the main contribution is iterative deepening, and that's what I'm going to start with. So before I go into that, though, I just wanted to give you an idea of why LRTDP, as it used to exist, does not have a very good anytime performance in finite horizon MDPs with large horizons, okay? Or at least why it can be improved significantly. So the way LRTDP works is it runs a series of trials, sort of like UCT. So in the current state, it's 0, but it takes the action that seems best at the moment, updates the value of 0, transitions to a new state, just samples the state from the transition function of the action it picked, you know, transitions to another state, and so on and so on. It samples these trials. At the beginning, these trials are quite long. You know, they're length h. Yeah. So what happens is, so it will sample a few of these trials, and then bang, you're out of time. When LRTDP halts, when given little time, it essentially halts with nothing useful. Because all it has done by that point is explore the state space just a bit, maybe